In the text in this chapter, I explained the theory behind how you compute an eigenvector from each eigenvalue. And just as a quick reminder, the way that you do this is by taking the matrix and you shift it by the eigenvalue. So you say matrix A minus the eigenvalue times the identity matrix. And then we assume that that shifted matrix is singular, that it's reduced rank, and therefore it has a non-empty null space. And then the eigenvector that corresponds to that eigenvalue is a vector in that null space. So it's a basis for that null space. Okay, now what we are going to do here in exercise 5 is implement that algorithm. So eigendecompose a random 3x3 symmetric matrix, as I mentioned a couple of videos ago. This theory works for symmetric and non-symmetric matrices. Symmetric matrices are guaranteed to have real valued eigenvalues, and so they're just easier to work with for exercises like this. Okay, so random 3x3 symmetric matrix, and then get its eigenvalues. And then for each eigenvalue in a for loop, compute a basis for or find a basis for the null space using this function here, scipy.linalg.nullspace. Now, in theory, this is the eigenvector of this eigenvalue. Okay, and then what you want to do is compare this basis for the null space of the shifted matrix to the actual eigenvector that you got from computing the eigendecomposition using numpy.linalg.eig. Okay, and then let's see. You have to take into consideration that the vector values themselves might not be identical, but you do expect them to be in the same direction. So the norms could be different. There could be sign indeterminacies. So you're going to have to figure out a way to deal with that when comparing the output of this function to the output of the numpy.linalg.eig function for this matrix. And then what I explain in this paragraph is that if you run this multiple times, you're probably going to find some errors. And those errors are actually coming from the shifted matrix having a empty null space, which means that the lambda shifted matrix is still full rank, which is not supposed to happen in theory, and but it can happen on computers because of rounding errors, basically. All right, so that's going to be an interesting demonstration. I'll have more to say about this stuff when I get to this in the code. So here I import this null space function from scipy.linalg. Actually, we've used this function in an earlier chapter to calculate vectors in the null space of a matrix. Okay, so here I create a 3x3 symmetric matrix. I get its eigenvalues and eigenvectors. And here in a for loop, I am shifting the matrix. So I say A minus this eigenvalue times the identity matrix. So shifting the matrix. Now we know that this needs to have a null space. So I compute its null space and I get a null space vector. And the way that I chose to compute a match between this null space vector and the eigenvector is to compute the correlation coefficient. And the reason why I did that is because the correlation coefficient is mean-centered and variance or vector norm normalized. So that is going to account for possible differences in scaling or differences in sign, because here I'm just going to report the absolute value of the correlation. Okay, so in theory, we would expect these all to be 1, and then we say, okay, maybe they're not all going to be exactly 1 because of some computer rounding errors. So, something like 0.96 is certainly a reasonable correlation to expect. 0.71 is kind of weird. It's a bit low. And let's run this again. Oh, there was 0.1. Okay, actually, this is a perfect example. This is really what you expect to show a match between the theory and what gets implemented in code. And, we allow a little bit of variability for computer rounding error. Okay, and here, this is perfect. This worked out perfectly. As I wrote in the book chapter, you will find some cases like this where, you're going to get an error message. And what is causing this error message? Well, we can investigate this. We can look at null v and see that this is actually empty. So in this case, we shifted by an eigenvalue and we got a non-empty null space. So we can also see the rank. What is the rank? numpy.linalg.matrix rank of this shifted matrix. Oops, sorry, this should be a period there like this. Okay, so the rank is 3, but we know from the theory of eigenvalues that this is supposed to have a rank of, well, it could be 0, 1, or 2 in theory, depending on the numbers in A and so on, right? But we certainly don't expect it to be 3. We expect it to be 2 or smaller. And there's nothing wrong with the theory of linear algebra or the theory of eigenvalues. This is really just one of the many issues that can arise when using finite precision computers to implement very sort of detailed, tricky mathematical operations. So one of the conclusions here is something we discussed in earlier chapters, for example, the chapter on least squares fitting. And that is, you should always trust these algorithms here. This is the stuff you learn in a textbook and on chalkboard and when you're writing math down on a piece of paper with a pencil. But then it comes time to implement mathematics on computers. And, you have to implement things in different ways to make sure that the numerical results match the theoretical results.